Speaker is the same speaker from just that last paper, Dr. Quanlin Lee, and he's going to be presenting. Well, Colleen Tarau could not be here today, so he's going to be presenting on his behalf, although they're both authors of this next paper. So again, Dr. Quanlin Lee has more than 8 years of R&D experience in the areas of two-phase flow and heat transfer and thermal fluid management system development. He received his PhD from Case Western Reserve University, developing an integrated variable conductance heat pipe for spacecraft heat rejection applications. Since joining ACT in 2016, Dr. Lee has been actively involved in multiple SBIR, STTR programs to develop cutting-edge thermal management solutions, including a two-phase heat exchanger with thermal storage capability, a titanium water heat pipe radiator for kilopower system cooling, a venting-based cooling system for 24-hour survival of Venus lander, a thermal concept for Europa ice melting probe, and an advanced hot reservoir variable conductance heat pipes for planetary landers. Welcome back, Dr. Lee.
Thank you again for the introduction. Hi, everyone. It's me again. I'm going to present the slides on behalf of my colleague, Colleen Tarau, who is the PI of this SBR program funded by JPL. Thermal management system for ice melting probe for Europa missions. So the outline for my presentation today is like this. I'll give you a quick background about Europa mission and the ice melting probe we developed. And we will give you an overview about the thermal management architecture and the feasibility study, including all the features we propose in the proposal. And then I will talk about the subscale prototype to demonstrate the concept. Some selected features will be demonstrated, and I will show a video of testing from that prototype experiment, and draw a conclusion and talk about the future work about phase 2. Just give you a side note, this program was successfully funded from phase 1 to phase 2, and we are already start working on phase 2 program. So NASA has a very high interest to explore Europa because Europa so far has the highest probability to finding life. And the main reason is that there's a liquid ocean, a huge liquid ocean underneath a thick layer of ice. But to be able to collect the data or collect the information from that ocean, first thing you have to penetrate the ice and access to the oceans. So we need to develop a vehicle that can penetrate the ice that's very thick. I'll talk about how thick that is. And we know there's some active mission so far to learn about Europa, like Clipper mission will collect more ground truths on Europa. By 2033, NASA expect to start penetrating the ice and start collecting data underneath the Europa ice shell. Not only for Europa, the melting probe we develop are applicable to other icy moons, such as Enceladus, Ceres, and Titans. And we will talk about that too. So the design requirement for the ice melting probe provided by JPL is like this. The melting probe diameter is around 23 to 26 centimeter. And they want to use the waste heat of RTG to melt through the ice. The power source will be 32 GPHS modules, and available thermal power on board about 8 kilowatts to 9 kilowatts. The environmental condition on the Europa makes us makes the thermal management design more challenging. One challenge is coming from pressure, because we want to move the probe laterally by liquid displacement, but because the environment pressure within the ice becomes extremely high, we need to figure out a way to provide some lateral steering capability when the pressure of the environment is higher than the supercritical pressure of the water. And also the thermal management architecture need to maintain the thermoelectrical end within the range that JPO said 50 to 100 degrees C, and the probe exterior surface should be maintained with this 25 to 30 degrees C range. So we have to come up with a very good thermal heat delivery system and the management system that will allow penetration of Europa ice layer. Other challenge, as you can see from here, the ice layer for the Europa surface is about 40 kilometer and it's significantly subcool, 100 degrees C. So with that temperature, there's a big chances that the probe will refreeze from the side. Lateral refreezing will cause the probe to be stuck during the melting process. So we have to come up with a way to mitigate this kind of risk during the penetration process. The other challenge will be the probe encounters some unmeltable obstacle like rocks or debris. So the probe need to have some lateral moving capability, or you need to develop some steering mechanism so you can change direction of melting without using any moving part, ideally. And the other thing is the melting process will take a lot of time. As JPO predict, it will take like two or three years to reach the bottom of the ice. And there's some trade-off to increase the speed of penetration. For example, you can increase the power, but you will need more GPHS modules, and that will cause the increase the mass and the volume of the vehicle. And you also want to minimize the cross-section area to speed up the melting process. The other thing is, during the normal operation, you want to use as much as heat for melting instead of wasting heat melting the side. So waste heat distribution for full melting is very important. That's why we propose to use a feature called variable conductance wall, which I will show in the next slides. So this slide shows the ice melting probe proposed by ACT, the thermal design. Figure on the left is a detailed design with 3 stacks of GPHS modules. And we proposed first feature use the pump two-phase heat delivery system to collect waste heat from the GPHS module and deliver to the front, the nose of the vehicle. Over there's a front vapor chamber. So GPHS, the pump two-phase condenser will have a heat exchange with the vapor chamber, and the angular space between the inner shell and the outer shell of the vehicle will be our variable conductance wall, which is another feature. This is a very important feature. Will provide the lateral melting capability and autonomy capability. And you can see there's 3 pressure vessel that is a liquid displacement system to provide some lateral motion to change the direction of the probe. Figure on the right is a simplified version, just showing the thermal management systems. So as I said, the pump two-phase system will collect waste heat from the GPHS modules and deliver it to the front where there has a condenser, pump two-phase condenser, and there will be a heat exchange, two-phase heat exchange between the pump two-phase condenser to the front vapor chamber, which is actually the melting front. And the angular space of the vehicle will be the variable conductance wall. The operating mechanism is very similar to the variable conductance C-pipe. So when the probe meets the obstacle, the temperature of the vapor in the vapor chamber, temperature and the pressure will increase and push the front upward, so that the heat can be melt going to the ice laterally, so that you can release the probe from getting stuck, or when the probe meets obstacle, you can heat up the entire probe will be heated up by the vapor. And with that liquid displacement system, we should able to change the direction of the probe and move it in a different direction to avoid obstacle. So this slides just kind of repeated, talking about the features. So first feature is the pump two-phase system. The reason to have that pump two-phase system is to minimize the delta T between the thermoelectric cold end and the vapor chamber. And because the pump two-phase system, you can use a very small amount of power for pumping, and you can provide very isothermal surface for all the evaporator, and all the loop will have a similar temperature. And the vapor chamber at the bottom will be the most efficient way to deliver heat to the entire nose. It will collect heat from the pump to phase condenser and uniformly put the heat to the front of the vehicle. Use a very small thermal resistance. And the variable conductance, just like I said, it will offer a passive lateral melting capability when it's needed. When the vehicle meets obstacle, or when the vehicle is stuck because of refreezing, it will melt laterally and without any additional control system. So we call it autonomy feature for this vehicle. And during the transition from Earth to Europa, this variable conductance will allow the entire probe to be, entire outer surface of probe become a rejection surface. So it can remove heat from the entire probe because of the variable conductance wall features. Liquid displacement system is the system that will allow the probe to move laterally to avoid obstacle. And we also propose to have high pressure liquid water jet cutting system to create ice, to break the ice to the front, so that we can minimize the power to melt the whole ice. In phase one, we successfully demonstrate the feasibility from feature one to feature 4. And in phase 2, we will do some investigation in feature 5. This slides give you some idea of the heat transfer paths for the system. Again, heat is generated from the cold end of GPHS modules going to the evaporator, and then the vapor will go into a condenser. Then it has a two-phase exchange between the pump two-phase condenser and the vapor chamber at the front. And then the vapor will deposit the waste heat into the inner surface of vehicle and to the surrounding, which is the ice. And there has a parallel path that will only activate it when the probe meets some obstacle or probe is stuck. So when the probe cannot moving forward, cannot melt downward, the variable conductance wall will start operate and start melting in the lateral direction and release the probe from getting stuck. So in phase 1, we need to do some preliminary study showing that the concept is feasible. The way to do it is to calculate the thermal resistance, all the thermal resistance within this chain. All the component will be designed, and the delta T resulted from 8 kilowatts of heat. So this slide shows the pump two-phase evaporator design, a concept. So this is a very similar concept as JPOs did. Separate two-phase. Liquid line and vapor line are separated by the wick structure, which can be shown on the top view of evaporator. The liquid line is going around the evaporator, circulating all the time, and vapor will generate it from the evaporator, taking heat from the thermoelectric converter, and then it will coming down and condense in the condenser. And then go back to the accumulator and pump it back from on the bottom of the vehicle. And here's the specs of the evaporator design for this full-scale systems. And this slide shows the condenser, how we engage condenser, pump two-phase condenser and the vapor chamber. The copper each color in this slide is the pump two-phase condenser. Each of the channel is actually the ring stacking from inside to outside, and there's about 10 rings in here to maximize the heat transfer area. So vapor coming from the pump two-phase vapor lines will start condensing inside those copper channels and become liquid. And this rectangular channel will separate liquid and vapor phase due to gravity. And the liquid phase will go into the accumulator and then into a pump, go back to the evaporator, pumping back up to the evaporator. And the yellow color, yellow volume in this vapor chamber is the vapor phase. So this is a heat exchanger between the pump two-phase condenser and the vapor chamber. Vapor chamber vapor will start condensing at the side wall, at the wall, inner wall of the vehicle, and dissipating heat to the surrounding ice with a very low thermal resistance. And you can see the extension of vapor chamber is the annular gap, which is for the vero conductance wall. So the vero conductance wall vapor is equal to the vapor chamber vapor. They are the same. Here's more detail about the vapor chamber design. As you can see this 3D diagram, like I said, there's a ring configuration for the pump two-phase condenser. We have a screen for liquid return. The reason for that compartmentalized design, because we need to make sure that liquid can return back from the condensing surface for the vapor chamber, condensing surface back to the outer surface of pump two-phase tubings. Figure on the right shows the calculation showing that the capillary limits of this vapor chamber design is higher than the 8,000 watts of heat, so we should able to we should able to return liquid without drying out the vapor chamber. And another challenge we identify is that there's a huge delta T between the outer surface of the probe and the environment, because the heat transfer coefficient between those are very low. So to mitigate that delta T, we come up with some area enhancement feature. In other words, an extruded fin structure outside of the vehicle that will minimize or decrease the heat fluxes and decrease the delta T. So this slide is summary of the thermal resistance from the cold end all the way to the melted ice. The delta T through each component also listed here. The delta T between the cold end of thermoelectric to the melted ice about 61.4 within the range that NASA expected. So this is a good design. We also through this exercise to identify how can we improve those components. So in the phase 2, we will start optimizing each component and further reduce the delta T as much as possible. Next feature I would like to talk about is the variable conductance wall, which is a feature that will offer autonomy of the vehicle. Like I said, this is the model prediction. When the probe meet the obstacle or it was stuck in the ice, the vapor temperature will increase and the vapor NCG front will be pushed upward. That will increase the surface area for heat dissipation. Then the heat can be rejected from the side of the vehicle and remove and start melting laterally. This will help the probe to release itself from refreezing. And also, when the probe meet obstacle, all the surface of the probe will be heated up by the vapor and assist with the liquid displacement system. The probe will be able to move laterally and avoid obstacle. So the liquid displacement system is shown in here. There are several ways we can achieve this lateral motion. The idea is to pushing liquid out from a vessel, as shown here. They can be achieved by thermal cycling, heating up by the electric heater, cooling by a cooling coil. So that will generate vapor to push liquid outward. And by controlling the valve, we should be able to change the direction of the probe. But as I mentioned previously, because that pressure, environmental pressure of the Europa ice will be significantly large as the probe sink beyond 70 kilograms. The surface pressure will be higher than the supercritical pressure of vapor. That at that moment you are not able to generate vapor within the vessel. So in that case, we will be changing the concept into a compressed liquid instead of pressure-driven. It becomes a compressed liquid-driven process. And the figure on the right shows some simulation about the efficiency of lateral motion using a different method. So that is the feasibility study. Now I'm going to talk about the lab scale prototype developed in phase 1. This is the CAD model drawing showing the probe size about 3-inch OD and 11-inch long. We incorporate 4 features in this subscale prototype. At the bottom is the front vapor chamber, which is simplified design using just a simple screen to return working fluid from the bottom to the heating surface. So heater you can see on the right-hand side. And the annular space between the inner shell and outer shell is our variable conductance wall. So we will demonstrate that features through the video. And the third feature is a liquid displacement nozzle or liquid displacement system for lateral motion. However, we are not able to demonstrate it by experiment because we have a very stiff feed-through at the end of the probe. And at the bottom of the probe, there's area enhancement feature to increase the heat transfer area between the probe and the surrounding ice. So here's some photograph showing the subscale prototype developed in phase 1, including the heater block in the inner shell and the weak structure of the vapor chamber, liquid return, and on the right-hand side, you can see the outlet for the liquid displacement system and the feed-through on the top of the vehicle, at the top of the probe for the liquid line, as well as the wiring for thermocouple and the heater block. The bottom shows the area enhancement fin structure, which is made by 3D printing technology. To test this probe, we also built up an ice system, which is pretty straightforward, a big chunk of ice using the 6 panels of serpentines to provide heat guarding. So the temperature of the ice can be controlled nicely using the liquid nitrogen. We successfully achieved minus 160 degrees in phase 1. And the figure on the right shows the instrumentation for the testing. In addition to thermocouple attached on the probe, we also have a penetration depth sensor used to measure the length of penetration. And in addition to that, we also have a camera putting in the front of the test setup to capture the process of penetration. So I'm going to show you the video here. This is the picture taken during the testing. The screen in the photograph, you can find information about depth of penetration, elapsed time, and the temperature profile along the probe. So that is a very important information you need to pay attention because you can see the front, the functionality of variable conductance wall during the penetration process. So this slide shows the temperature as well as the depth of penetration. In the beginning of penetration, the temperature looks okay and the probe moves smoothly. And at certain time, because of the refreezing, the probe getting stuck. You can see from the penetration data, it becomes flat. At that moment, you can see also from the bottom that vapor temperature start to pushing up and start releasing the probe itself without any additional operation. So we call it self-releasing mechanism by the variable conductance wall. And it happens every time when it's getting stuck. Vapor start to heating up the sidewall and release the probe autonomously. And the second test we did is similar, but at the end of test, we also put an obstacle, embedded obstacle in the ice, and eventually the probe had meet the obstacle. And that when that happens, vapor temperature start to increase and occupy the entire length of the sidewall. So now I'm going to show the video. Sorry for that. Let's try again. So paying attention on the temperature profile in the screen when the probe getting stuck, you can see that the motion of vapor. And also paying attention when probe is self-released, vapor will drop back to the front, will be focused back to the front of the vehicle. And at the end of the test, the probe meets obstacle and the vapor from keep pushing up. That is the demonstration of the variable conductance wall. And this slide shows the front location at different scenario. When the vehicle is operating normally, the front is located at TC, location 14. And when the side starts refreezing and getting stuck, the vapor front will start propagating and going upward. And when it meets obstacle, the front location is expanded to TC 16. So I'm not going to read through the conclusion, but through this SPR phase 1, ACT developed a thermal management architecture that for Europa ice melting purpose. And this thermal architecture involves multiple new features that will help the melting probe to melt efficiently during normal operation and also mitigate some risk that can happen during the melting process, penetration process. Those features including a pump two-phase heat delivery system, a front vapor chamber, and a variable conductance wall to autonomously change the lateral melting capability and assist with liquid displacement steering system. We are able to move the vehicle when there's an obstacle in front of the vehicle. And in phase 1, we did the preliminary design and assess the feasibility by calculating the total delta T between the thermoelectric cold end and the environment, and that is a 70 degrees C. And the password to improve also identified it. And in phase 1, we developed a lab scale prototype, incorporated several features. The most important feature including vapor chamber with area enhancement, fin structure, variable conductance wall. Unfortunately, we are not tested the liquid displacement system, which will be tested in phase 2. And we do some testing using the self-made ice penetration block. And we show some functionality of the variable conductance wall as well as the front vapor chamber concept. So the future work for this program will be full-scale prototype. Will be developed a realistic full-scale thermal probe, and we will optimize all the features, test all the features, and develop at least 2 prototype at the end of program and deliver to NASA JPL for further testing. So this is my last slide. I would like to thank both financial and technical support from the program from SPR program JPL, and thanks for the technical monitor Terry Hendricks and Eric Snada for their inputs. And also thanks all the people from ACT. A little bit long, sorry, but I would like to take some questions from here.
Yeah, thanks, Dr. Lee. Hey, Bill, do we have any questions?
Well, we had one question about requesting an explanation of how the variable conductance wall helps when there's an obstacle in front of the probe. The person who asked the question said that the presentation later answered that, but if you'd like to comment more on that, feel free.
Okay, so I'll just talk about that again. So to avoid obstacle or to mitigate the chance of meeting to dodge obstacle, the variable conductance will need to work with the lateral liquid displacement, lateral steering system. So the variable conductance will heat up the entire probe, but the liquid displaced systems will change the direction of the probe to avoid obstacle. We are not able to demonstrate it in phase 1, unfortunately, but in phase 2, we will definitely do it.
Well, Warren, the chat looks pretty quiet.
Okay.
We'll turn it back over to you.
Well, so the context presented today, also you can find it in the ICS paper recently published. And if you have any question about the concept or the video, please feel free to reach out to me or Colleen, anybody in ACT. We are happy to give you more explanation. Thank you.
Yeah, thank you again, Dr. Lee.